In this tutorial, I want to demonstrate how to perform a complete first-order thermal analysis for this beam expander design. We want to optimize the wavefront error for a system temperature range from -20 degrees to +80 degrees Celsius. This example demonstrates a beam expander based on a Kepler-type telescope with an expansion factor of 8. The system consists of two plano aspheric lenses, and the first aspheric lens here focuses the light to an intermediate focal point, while the second aspheric lens collimates the outgoing beam. Both elements are modeled as aspheric surfaces. You can also see them here in the optical design tree view. You can see here this Q-con form, and also for this first lens we have this Q-con form. In this tutorial, the initial system is defined at an environmental temperature of 20 degrees. And the objective is to demonstrate how to perform a thermal analysis over a specified temperature range, for example, from -20 degrees to +80 degrees. The first step in performing a thermal analysis is to create a multi-configuration setup, for example, with 3 configurations. We define a parameter called temp, which represents the system temperature. For the 3 configurations, we assign the temperature value across the desired range. So for example, from -20 degrees to +80 degrees. And let's choose a value that lies in the middle. So for example, +20 degrees. In the next step, we need to link the temp parameter to the environmental temperature of the system. So for that, we go to System Setup, here for Environment, and there we add, here for temperature, we just insert here this parameter. And when switching here between the different configurations, you will notice the defocus and a change in the wavefront due to the different temperatures that we have defined here. And this defocus occurs because the temperature changes affect the refractive index of the lens material. And in this example, the materials used for our lenses is material F2 from SCHOTT. And when we have a look in the materials catalog for this F2 material of SCHOTT, you can see that the F2 material provides these thermal parameters that define how the refractive index varies with temperature changes, and these parameters are used to calculate the resulting optical changes. And if those thermal parameters are not defined in the material, a thermal analysis cannot be performed with this material. By the way, if we want individual lenses to have a temperature different from the overall system temperature, we can activate the isThermal parameter, and you can find this parameter here in the next to the material, in the material row. And here you can see this isThermal checkbox. You can find it also here in the material row. And this allows assigning a separate temperature to a specific optical element. However, we will not use it in this tutorial, so we will deactivate it again. I will just mention it here for the completeness. And maybe also what's important, or could be an important information here in the system setup, we can add a sub-environment to this main environment just by clicking here with the right mouse button and then click on Add Local Environment. And this allows lenses to be placed into different environments so that they inherit the corresponding environmental properties. I will delete it again because we won't use it in this tutorial, just mentioned here for completeness. So far, we have only considered changes in the refractive index due to temperature variations. However, when the temperature of the environment, and therefore also the lens temperature, changes, not only does the refractive index change, but of course the lens also physically expand due to thermal expansion. And the thermal coefficient of expansion, which describes this physical expansion, can be found again here in this materials catalog. So go to our F2 SCHOTT material, And there you can see this TCE, so the thermal coefficient of expansion. And if this coefficient is defined, the lens will expand or contract accordingly when the temperature changes. And this thermal expansion coefficient can be applied independently of the surface shape. So it is therefore not limited to spherical surfaces, but can also be used for aspheres, freeform surfaces, and any other surface types available in Quadoa. And to consider thermal scaling, we need to go to our optical design editor, and then here in the material row of the element, you can see here the scale thermally checkbox. And we need just to activate here this scale thermally checkbox for the respective lens. We can use it also here for this material, for the lens 2. This makes thermal scaling very straightforward just by activating here those scale thermally checkboxes. And as also can be seen here in the wavefront false color plot, the wavefront changes when we disable or activate here this checkbox, since the lens expands with the temperature. Maybe just for illustration, let's add another configuration here with a temperature of 1000 degrees. And when we switch here this configuration, meaning the lens temperature is set to 1000 degrees, and we zoom here into our 3D view, you can see that the temperature from -20 degrees and to 1000 degrees expands here the lens. You can see how the lens moves to the right due to thermal expansion. In the next step, we want to consider not only the expansion of the lenses, but also the expansion of the mechanical mounting. And for visualization, I've implemented a very simple mechanical mounting here, this purple mechanical file or part. Each lens is mounted on both sides using a seat mount. So when we hide here this lens, we can see here this seat mount, and on the other side we have here this green ring that holds the lens in place. And the same mounting applies here for the first lens. This means that when the mechanics expand thermally, the distance between those two mounting surfaces changes accordingly. And to consider the thermal expansion of the mechanical mounting, we define a thermal length in the multi-config lookup table. So we click here on this add a thermal length. And since we want to keep the intermediate focus unchanged, we introduce two thermal lengths, and we name them length 1, and the other name is length 2. In the temperature parameter field, we specify the source of the temperature by using the parameter temp. And this parameter temp defines the system temperature and therefore as well the mechanical temperature. Next, we set the nominal length at the reference temperature. So our nominal or reference temperature is 20 degrees. At this temperature, the distance here is 10. So we just copy and paste here this distance of 10, and as well here for the length 2. So for our lens 2, we just copy and paste here this position C and paste it here for the nominal length at 20 degrees. Next, we assign a material to the mounting. You can either define a custom TC material, so you can just manually enter the expansion coefficient here manually, or you can use from the drop-down different types. You can also use here from model. There you can just use, for example, the same material type as from other lenses, for example. But in our case, we want just to use here standard steel. So just select here steel for both materials. And finally, we replace the existing C positions here for both elements with our thermal length parameters. So here length 1 and here length 2. So let's change the temperature to see what happens with our system. So at the nominal temperature of 20 degrees, the system matches the original geometry. So we have here 10 millimeters and here 74.62. At minus 20 degrees, we can see that here the length 1 position C decreases to 9.9 and also here to 74.5. And when we click to 80 degrees, we can see that here the values increase to 10.007 and 74.67. And in the extreme case, so let's go here to 1000 degrees, you can see that the values increase further due to the thermal expansion of the mounting. In the next step, we optimize the system so it performs well across the full temperature range from minus 20 degrees to plus 80 degrees. At the moment, the system shows about 1 lambda defocus here for the minus 20 degrees, and for the 80 degrees, it shows a defocus of 1.6 lambda. And the goal is to find a good compromise so performance is balanced at both temperature extremes. And to do this, we add a new merit function here in our system setup. So we go to this optimization, and then we click with the right mouse button, add merit function. We name this merit function thermal. Then we open it, and we open here our ray trace. And as trace goals, we add our wavefront RMS error. We then duplicate here this ray trace and assign different configurations. So here configuration 1 for minus 20 degrees. For the second ray trace, we will use configuration 3 for the 80 degrees. And when we open here the trace goals, we can already see that we have here different values for those wavefront errors for those both minus 20 degrees and plus 80 degrees. And these deviations are caused by a thermal expansion and changes in the refractive index. For the optimization, we now need to define the variables for the merit function 3 we just created. For that, we will select here merit function 3. And our goal is to move the lens 2 along its optical axis in the C direction. And to do this, we activate the variable checkbox for its position C. And as here the position C refers here to the length 2 parameter in the multi-configuration, we'll just click here in the multi-config and we will activate here this variable checkbox. And this allows the optimizer to adjust the position and find a good compromise between the different wavefront errors. And next we go here to optimization, then we click on local optimization. Here we will select from the drop-down our merit function 3 for thermal. And then we will just click on optimize. And we can see that here our optimizer did his job. So we found a better value. And when we look at the wavefront error afterwards for minus 20 degrees, we have a defocus of 1.3 lambda for minus 20 degrees. And for plus 80 degrees, we have as well a defocus of 1.3 lambda. So this represents a well-balanced compromise across the full temperature range from minus 20 to plus 80 degrees. And with this design, the system shows a maximum defocus, as mentioned, of about 1.3 lambda, while taking all important thermal effects into account. So expansion of the aspheres, changes in the refractive index due to the temperature change, and the mechanical expansion of our mounting. So in other words, all key influences are included here in our thermal analysis, resulting in a complete first order thermal analysis. Thanks for watching.